All right, so we've kind of already done this. We've been doing this, but I'm going to go ahead and just do another one because why not? Let's say we have a sinusoidal source. Say we have a voltage divider here. And we are interested in the, let's just make this 50 ohms. Let's make this 50 ohms also. And let's let this be a sinusoid Vs of t. And let's say Vs of t is equal to, let's just say 1 volt times, 1 times the sine of omega t volts. Okay. Or just the sine of omega t. And we're interested in determining the current. Oops, let me grab the red. We're interested in determining the current here, I of t. And then we also want to determine the power, the average power dissipated by this second 50 ohm resistor here. I should go purple since I've been sticking with purple for power and, you know, blue for voltage and red for current. I want to stay consistent. Let's call this V O of t or V out of t. And let me just go purple around this and say that we're interested in the average power dissipated by that resistor. Okay, so what will we do first? Well, first we need to determine the current. Pretty straightforward. The current in the circuit is going to be the voltage Vs of t, or just sine of omega t, divided by the resistance in the circuit, which is 100 ohms. Okay, and so that's going to be equal to 1 over 100, or basically 0.1. Nope, 0.01. If I want to do amps, or I could just do 10 milliamps again. Let's do 10 milliamps. I'm sorry, I'm struggling. Times sine of omega t milliamps. Okay, so that would be the case, right? 1 divided by 100 definitely gives me 10 milliamps. Yes. Okay. Sorry. So now I need to find my average power. I have two options. I could obviously take these two and find the instantaneous power, which would just be P of t is equal to sine of omega t volts times 10 sine of omega t milliamps, which would give me P of t is equal to 10 sine squared of omega t milliwatts, which would give me 5 times 1 minus the cosine of 2 omega t milliwatts. And that would be my expression for the power, the instantaneous power. And then I can go ahead and take the average value of that, and I would get some value, right? Or I can use RMS values. Since this is a purely resistive load, I know that the voltage and the current are in phase. I know the RMS value of a sine wave is just its peak value divided by √2, right? So if I'm looking at my voltage waveform here, it's swinging up to a value of 1. And if I look at my current waveform here, it's swinging up to a value of 10 milliamps, right? And so the RMS value of this one, VRMS, is equal to 1 over the square root of 2. IRMS is equal to 10 milliamps divided by the square root of 2. And so if I get, this is 1 volt divided by the square root of 2. If I go ahead and compute my P average, I am going to get 1 volt. Oh, sorry. I'm making a huge mistake here. The fact is this is the average power dissipated by both resistors, because I took the voltage across the entire thing instead of just the single resistor. Okay, well, I hope that you could quickly help me realize that, and we can follow that. Since it's a voltage divider with equal valued resistors, this would be half sine of omega t. This would go to 5, and this would go to 2.5. and that would be the only difference. And so then this signal that I was actually talking about would be at 0.5 volts. That would put this at 0.5 over root 2. Okay, and we're right back where we need to be. And I should definitely color this blue so that we know we're actually talking about V out. Sorry about that. All right, so we're basically fixed. And now I can say that P average is going to be 0.5 volts divided by the square root of 2 times 10 milliamps divided by the square root of 2. And I get that 10 times 0.5 is 5 milliwatts divided by 2, which gives me 2.5 milliwatts is my average power, okay? And that makes sense because, again, this signal, this power signal, when the cosine is at -1, then this entire inside term here is going to go to 2, so it peaks at 5. And when the cosine is 1, then this whole term goes to 0, and it's 0. So this power signal is basically swinging between 0 up to 5 milliwatts around an average value, and that average value that we just calculated is 2.5 milliwatts, and that's the power dissipated by this 50 ohm resistor. Because the same current and the same voltage would be across the other resistor, you could prove exactly the same, that the average power dissipated by this resistor would also be 2.5 milliwatts, and so then the entire circuit dissipates 5 milliwatts. Okay, so that's my little resistive load example. Sorry for kind of making it a disaster by screwing up the values that I used, but hopefully that was useful. I think I have another slide here just in case I needed more room. Maybe on the other slide I can go through and do the derivation using the integral, just in case people prefer that to the VRMS, IRMS method. I'll just do that. So I'll end this video here, and then I'll find the average value again, but using the average value formula and taking the average value of this function P of t that I found, and we should be able to see that we get 2.5 milliwatts again. And then after that, we're going to move into the next case, which is where the load is not necessarily resistive, and we have to take into account the phase shift between the voltage and the current. Okay? One more thing that I don't like about this slide is the frequency of the current looks a lot slower than the voltage. All right, now they look the same. All right, I'm going to go ahead and end this video.